All right, folks. So this is a solved problem. You're going to work on that so that we have a mass spectrum here. Let's propose a molecular formula for this compound. In this case, I didn't give you any hints, right? You don't have any multiple choice options. So you're going to have to do the whole shebang. So what's the M? 150. That's your M plus peak, right? Okay. That's the mass of your compound. Yep. It's mass. All right. So, do we have anything special about this?
2 peaks plus bromide. That's M.
Yeah, we got an M plus 2, don't we? And so it's almost the same height. So very likely something like a bromide or a chloride, right?
If you have multiple bromides, like based on that peak, or
You could. Yeah. In fact, it would actually have the exact same rules. Remember the formula I gave you for the isotopic ratio? You can do that same isotopic ratio for anything. Yeah. So like if you have you think it's a chloride, you could plug them in and see if that would give you something that would be like 2 chlorides. And what would happen is the bromides don't change much. They're almost 50-50, right?
Yeah.
So adding more just kind of,
yeah.
yeah. So it's like 52 instead of 51. But for the heights of these, if you look at something like a chloride, as you add more chlorides, you'll actually get more of them where they'll start showing up as more isotopic ratio. And so it'll make a small difference, not as much as the carbons did though. Because the carbons are a 1%, so you got a lot of room to grow. Yeah. But yeah, you can use that same isotopic ratio for all these. Okay. So, how do we figure out whether it's bromide or chloride, and how do we figure out how many carbons we have? You can look back in your notes. I did a whole problem where I helped you do that. There's a formula to figure out the number of carbons. In fact, I did problems for both of them, in fact. Can anybody tell me if you lose this double peak at some point in the spectra? So this one here, does that still have that bromide or chloride? Yeah, pretty obviously, right? Okay, how about these over here? Yeah, not as obvious if you have it or not, isn't it? So you definitely lost it here, didn't you? Definitely no double peak there. Okay, let's go ahead and go on now that hopefully everybody's made some progress and tested your understanding of the material a little bit. Okay, and so again you have the MZ equals 150. That's your M plus peak. That's your mass of your compound, right? You got the MZ 152, and so that's your isotope for a bromide or chloride, isn't it? Okay. So we have one of those. Now we go ahead and use our ratio right here, isotopic ratio. And you see that the heights were given to you here, 0.7 and 14.7, right? So we plug that into the formula, 0.7 over 14.7 divided by 1.1 times 100%. That gives you 4.3. That's going to be an estimate of the number of carbons, right? So the number of carbons should be something around 4-ish, right? Okay. All right, so we look at the M plus peak, and its mass is 150. That is even, isn't it? Right? And so is it very likely we have a nitrogen in there? No. If we have a nitrogen, it's going to most likely be odd. Okay? Almost certainly going to be odd. And that's because the number of things that connects to a nitrogen is an odd number, isn't it? Nitrogens want to make 3 bonds, don't they? Okay? So it means they make 1 less bond. We reduce the number of hydrogens then by 1, don't we? Okay? And so, again, we have about the same intensities. Now, this does strongly suggest we have bromide. We also don't have this huge mass here that could allow for a bunch of chlorides, right? That we would have these ratios shrink. So it's actually a very safe bet to just go bromide. Okay? If you wanted to try to figure out if it's chloride or bromide, the easiest way to do that is to look here. And we see our drop off here. We don't really have anything that corresponds to a 35, do we? See that? We have something that corresponds to like an 80, don't we? And that doesn't have the 2 peaks, the double peak, does it? They're almost equal intensity. Okay? And so what you'd end up seeing is, yeah, that probably is your bromide, isn't it? If we had something that corresponds to these 2 strong peaks like this, and it was up here, that would give an indication it might be a chloride, wouldn't it? That's only a small drop-off. Okay. Okay.
I'm sorry, I'm confused. Isn't the drop between the 150 and those other peaks, like that's like about 35, no?
This one here?
Yeah.
Yeah, but that has the double peak. That would be a chloride or bromide.
You know, I get that, but why wouldn't, wouldn't that make more sense to be a chloride then?
No. Because this drop here still has the chloride then. That's what you'd be saying. Is that you're dropping 35 by not removing the chloride. You're not removing this double peak. See, this double peak is because of a bromide or chloride?
The double peak goes away when the halogen goes away?
Exactly.
Oh.
Because that's due to the +2 isotope, isn't it? Yeah. So you would need to see that go away for that to be the mass of your isotope. Okay? Now, this is a bit more complex and a bit more difficult to use. The easier one is the isotopic ratio right here. And the bromide is nearly equal ratio, right? The chloride is only a 30% ratio. Okay? And so this one's very obviously bromide because they're almost equal, right? Really close. Okay? Okay. And so we go off onto the next part. So we account for our 4 carbon atoms. We account for our bromides. So we take in the 48, the 79. We add those together. And we go ahead and subtract that from the total mass, 150. And that means somehow we need to come up with 23 units, right? This isn't going to be a nitrogen because we had already eliminated the nitrogen as being a very low probability. Okay? And so we're not going to use any nitrogen there. So the next thing we have to do is, could we have oxygens? Could we have fluorines? Could we have just hydrogens? Right? What's accounting for that remaining mass? So the first thing you always want to start with is, does it make sense to do hydrogens? Would it make sense to fill in 23 hydrogens around 4 carbon atoms? No, it's really excessive, right? Does anybody remember how to get the number of hydrogen atoms that are saturated? a 2N.
Up 2 and plus 2.
So you take the number of carbons times 2, right? So that'll give you 8. 10 is the maximum number of hydrogens you're likely to see. Okay? That'd be the maximum number you can actually fit on this carbon skeleton. And so this number obviously is just ridiculous, right? No way, not possible. Okay, and so we have to somehow put in an oxygen or a fluorine. Both of those don't have high isotopic ratios. Both of those would not really affect the overall number of hydrogen and the balancing of that. So they wouldn't change whether it's odd or even. Oxygen, because it has the 2 bonds, right? So it'd still end up being an even number. Fluorine, on the other hand, what's the mass of fluorine? 19. Okay. That's an odd mass, but what happens when you put a fluorine on? What happens to the hydrogen where it was? You replace the hydrogen, don't you? And so effectively, a fluorine is a hydrogen with plus 18 masses now. Okay? So you still end up with even. Okay, so what we're going to do here is we would go ahead and write these out, and then we'd calculate their masses and see which one would make sense for this to be the remaining mass of our compound, right? And so we put an oxygen, mass is 16, right? Okay, and that would then give us another 7 mass, which would be hydrogens. And so that makes a lot of sense, doesn't it? Okay. Okay, how about this one over here with the fluorine? So fluorine's mass is? What's the number? 19. Okay. Okay. And so we would take our 23 minus 19. That would give us a 4, right? And so we would have 4 remaining that are hydrogens, which would give us the formula there. Okay? And so both of these are possibilities. Both of these would answer our problem here. Could be either of them right now. We don't have the remaining information that would allow us to solve that yet because I need to get you up to a certain point, right? Okay. Okay. Does anybody have any questions of how I solved this up to this point? Does everybody realize this is basically just puzzles? Okay. Okay, so again, we've primarily so far focused in on our M plus peak, a little bit of information on the isotopes on that peak, right? We've essentially ignored the rest of that molecule, ignored all the fragments, ignored all the fragmentation pathways. So if we want additional information about our molecule, that's where we're going to have to look, and we're going to have to start using those. Now, we can get a lot of additional information, in fact. If I made a positive charge on a molecule, typically that's called a carbocation in this course, right? Okay. Where did the carbocations always end up at? Well, yes, but do they end up on primary carbon, secondary, tertiary? Tertiary. Between a secondary carbon and, say, off of a nice benzene ring substituent, which one would you end up off? Yeah, next to the aromatic, right? Okay. And so this tells you a tremendous amount of information about these things in the fact of what fragments off, right? If you get a fragment that's same as an ethyl, then that tells you that, well, that ethyl fragmented off, and that was a fairly stable orientation if the intensity is high, right? Okay. So again, these fragmentation pathways are the same chemical processes that are responsible for producing the fragment ions, the same processes that we've talked about every time we've been talking about stabilities of carbocations, isn't it? And so it's that same methyl hydride shift information that we'd always been working on. Okay? All right, so it's going to depend on your structure of your molecule and your functional groups, of course. And so right here we see a nice example of this. So here's the compound here, and this is the M+. It has a mass of 86. Everybody see that okay? Okay. All right. Now, what does this base peak tell you? What is that base peak always going to end up being? Mm-hmm. It's the most stable of the carbocations that are generated, right? And so it tells you what's most stable. What do these ones tell you? Less stable, but still pretty stable, right? This one here, not stable, right? Yeah, definitely not a stable one. Okay. And so what we're going to see here is that we get this right here, which is the carbocation on the entire structure. We haven't fragmented it all. That's the parent molecule, right? These ones down here are going to be fragmentations of that, aren't they? They're going to be where we have parts of this split off because of rearrangements. All right, so remember that whenever we draw these out and whenever we talk about these, is this ever detected? The free radical neutral? No. No, we ignore that, right? Who cares? Go away. Okay? Because this is neutral. It's just going to not bend. It's going to slam in the wall and get pumped off, right? So that's going to go away. The only one that can make that turn because of the magnetic field that's involved is something with a charge on it, right? Specifically a positive charge. And so only these ones with the positive charge on them can make that turn. Okay, so this right here would be the butyl cation. It's 57. Notice what it matches up to. Yeah. And so that's actually the most stable one. That's the one that's likely to form the easiest. Okay. Okay, so this right here would be your methyl ion. This would match up to 15. Notice which one that is. That's that one right there, right? You wouldn't expect the methyl with the positive charge on it to be very stable, would you? And so if you think about it even a little bit, it makes a huge amount of sense that you have barely any peak, right? That's not the pathway that's going to be the most stable. Okay. Mm-hmm.
So when this happens, like when it's put through the spectrometer or whatever,
Mm-hmm.
there's not enough time for the I forgot what it's called.
Shifts?
Yeah, the shift.
Yeah, so the shift can happen.
The shift can happen.
Mhm.
Okay, 'cause that was
Yeah,
like-
it would give you the same mass though.
Mhm.
So ultimately, these are drawn like this, but it doesn't matter where the positive charge is.
Okay.
So let's say this one right here. Why is this more stable? Is because it can actually put a positive charge here, right?
Yeah.
So we can have the hydride shift happen. It would give you the exact same MZ.
Mhm.
Okay? Is that making sense?
Yeah. Okay. So then, like, the other ones are just where it's cut at a different point. So there's.
Exactly. Yeah, and we just, by notation, leave the positive charge at the cut point. Yeah. Very likely, it's not actually that location is where it stays.
Okay.
It very likely rearranges onto these.
Yeah.
Okay, but it doesn't actually matter. They have the exact same charge to mass ratios. Okay. The hydride shifts are fast enough that you should probably be able to see them. Okay. Okay. All right, so this right here is the isopropyl cation being generated here. And this is this compound here being broken right there. Okay. We can see that there'd be a pretty big difference in stability for breaking it right there, right? Because that's a secondary carbon that gets generated right on. Okay. Okay, so what we see is the base peak here is 43. And this right here is the M plus here. Okay. Everybody okay with that so far? Okay. And so what we're losing here is the propyl radical. We're leaving the isopropyl cation. Okay. All right, so this is going to be your dimethylbutane here. Now, what do we see about this is that when we fragment this, this would actually be incredibly stable, wouldn't it? So when we generate a positive charge, this N plus here, this is not very stable. It just has the positive charge wherever, right? So in comparison to, say, this right here, this one's a lot more stable, isn't it? And so this peak here is much smaller than this one as compared to like this, right? The difference in stability between this carbocation just being anywhere on here versus it being here, well, that's actually considerably more stable, but not as more stable, right? Not such a huge difference. So what happens if you have an extremely stable position in terms of carbocations? Well, that M plus peak actually can completely disappear because that one's so high energy that your breaking becomes almost your entire population. Okay? Okay. So again, this one here, you basically can't see it. If you have this on high enough resolution, you might be able to see it. Okay? It needs to be very sensitive, though. It's not actually resolution, by the way. It's sensitivity, in case you're wondering the terminology there. Okay, so this one right here is going to be an alkene. And so what we see here is when we put the positive charge on it, we actually end up with a very stable M plus that's not fragmented, right? And so what you see is your M plus ends up being one of your larger species, more stable species. Okay? And that's why you see that one's almost like a 50%-ish, right? Yeah. There's still more stable spots like that, but this is very stable because you can actually just break this double bond, can't you? Okay. Okay. So the alkene's molecular ion tends to expel a alkyl radical from an allylic carbon. This is going to produce the allylic cation that's going to be in this form right here, where it has the double bond and then a positive charge off of that. And so what you're going to see here is this is the allylic carbon here being expelled. Again, this was that double bond that we created that positive charge on, right? And so we're going to go ahead and break fragment right here. That will give us the ethyl radical. And then we're going to have this remaining part right here, which would be your butene normally. And that's going to give you the butynyl cation right here, which has a nice resonance stabilized structure. Okay. All right, and you'll notice that in the previous structure here, this was the most stable peak. See the 55? Right there. Okay. Did I lose anybody there? All right. Okay, so let's look at the benzene and benzene derivatives here. So your molecular ion for the alkyl benzene here is going to tend to expel an alkyl radical from the benzylic cation, and this will give you the benzylic cation right here, which is your highest population. So what you're going to see is that we're going to break the extra stuff off, leaving a single carbon off of that benzene. Okay? Remember that the benzene, if we left the positive charge only on the benzene, nothing else, we would actually break the aromaticity moment. Okay? So it always ends up that position off of the benzene ring. Right? Same as the reactions. Remember the reactions that we did the same thing? Okay? It was always stabilized on that next carbon off the benzene, right? Okay. Okay, and so we fragment off here. This is going to be your propyl radical that goes away. This right here is going to be your cation, and that's the benzyl cation. It's the benzene substituted cation. And this is going to be our most stable. Its mass is 91. Please note that this actually can do a rearrangement here, which is the tropylium ion here, where you have a methyl rearrangement where this shifts up onto here. And because it has that empty p orbital here, it actually completes the aromaticity. This is one of the reasons it's so stable. Okay. Does that change the mass or anything at all? No, same mass, same charge, shows up in the same spot. Doesn't really matter, does it? Okay? But this is one of the reasons that's so stable, is because it actually can make this compound right here. If you actually do this fragmentation for some reason, you're going to see that. Okay? By the way, there's actually instrumentation where you would take these and then do another fragmentation to see what gets what results. Okay? Or you do other tests on your fragments so you can tell what resulted from it. So that's one of the reasons why I bring this up, but most of you probably aren't going to care. However, some of you will. So the alkyl halides, amines, ethers, and alcohols, many of these functional groups are going to be heteroatoms. Heteroatoms meaning not carbon containing, right? Something else than carbon. Again, these are going to play major roles in this. You may have noticed, for example, the oxygens tended to stabilize those carbocations, whereas you might not think they would, because they have those lone pairs and get sucked into bonds, right? And stabilize. So one of the most important factors of heteroatoms is always going to be the non-bonding lone pairs of electrons, because you can pull those in to double bonds with your carbocations, right? And then those help to stabilize the carbocations. So these are usually the least tightly bound electrons in the molecules. They're going to be delocalized electrons, right? Meaning they can move in and do resonance structures very easily. Okay? Localized electrons are trapped between two different things, can't really move around much, can they? Okay? So in the ionization of a molecule containing a heteroatom, the lone pair electron is going to generally be the most likely electron lost that will produce the molecular ion, that M+, because again, they're going to be the ones that are not bound between things, right? They're going to be drifting off on their own, and they're easier to access, they're easier to pull away, they're easier to move. So this right here is your loss of your non-bonding electron, and this is going to give you your M+. In this case, we'll end up with an M+2 as well, right? Okay. And it comes off of this chlorine right here, which then ends up pulling electrons from the carbon and can then leave, because that's going to make it a pretty good leaving group, isn't it? Okay. And so you see that one of the resulting fragments that ends up being very large amount of the sample is actually just the loss of the chlorine, isn't it? Okay. Oftentimes when you have things with lone pairs, especially things that are pretty good leaving groups in and of themselves, that have a fairly high electronegativity, they end up being your base peaks, or something very close to your base peak in height. Okay? It's just the loss of that bromide, the loss of that chloride, very common. Okay? And you actually probably noticed that in the previous, when you guys were asking me all those questions, and you noticed like the huge base peak. They only had one peak, right? Didn't have the two? Yeah. You were noticing the bromide and chloride being lost. Yeah. Okay. So the alpha cleavage. This is going to be the elimination of an alkyl group from the carbon atom that's bonded to the heteroatom. And so this right here, we have our heteroatom. It had lost the electron because it had lone pairs, right? Those were the easiest to knock off at first. And then we get the rearrangement. That's going to be the alpha cleavage, where the alpha carbon, everybody's comfortable with that terminology, right? Okay, so this would be the carbon attached, right? Okay. This is alpha, meaning the first carbon's next to it. Okay. This would be beta, and then so on down the Greek alphabet. Okay. Everybody good with that so far? Okay. Fantastic. And so these are both alpha cleavages. This would be the methyl alpha cleavage. This would be the ethyl one. Notice that this forms the double bond, which stabilizes the carbocation here. And this would give you your MZ91 and MZ77 peaks. And you notice those are fairly large amounts, aren't they? Okay. Everybody good with that so far? Okay, fantastic. Okay, so this is your alpha cleavage in a amine. And so we have the M plus here. See, it's 101 odd. And so automatically you should go, ooh, that kind of indicates we have an amine, doesn't it? Okay. We have an odd number bonding. And so we have an odd number mass, right? Okay. Okay, so we have here our indication of an amine. And what we see here is this lone pair right here would lose the electron very likely. That gives you your M plus. And then the most likely cleavage, if you're not going to lose the nitrogen, which losing the nitrogen would cleave it in one of these positions, right? Right here. So that would be a very large mass. That would be way down here. If you're not going to cleave the nitrogen, this is probably going to be where it takes the electrons from one of the alpha carbons, right? And so you'll have an alpha carbon being lost, one of these three. How do I tell which one it is? How much does the CH3 weigh? 15, yeah. Yeah. So I look here and I notice it's 15, right? That indicates a methyl loss. Okay? Okay. What would be the next carbon, by the way, in terms of mass? What's a methylene? CH2. 12 plus 2, 14, right? Yeah, so that would be an additional 14 if you lose an additional CH2 with it. Okay? Okay, so this is your ethers. Again, ether on either side, right? And so this is going to be your fragment ion from another alpha cleavage again. You'll notice actually here we get a very small M plus. Can you guys even see that? Good grief. You guys have an eye doctor? Insurance at all? No? Okay.
Don't bring it up.
Okay. I don't either. I don't. It's actually not worthwhile. It's kind of a bullshit insurance. Yeah. But yeah, yeah. I have a health spending account. That's what I have. All right. So again, we have the 102 here. Again, we have a cleavage right here. We end up with a 15 coming off. That's your alpha cleavage again, losing a methyl group. And there is a very, very, very small M plus peak right there that apparently many of you cannot see. So, okay. All right. So again, this is your alpha cleavage in alcohol. And so we have our M plus here. Notice that an alcohol typically does something kind of interesting and unique. Okay. If we made a positive charge on the oxygen, what would that do to the hydrogen? Make it super acidic, right?
Yes.
Yeah. And so what do you think happens to the hydrogens in these?
They go away.
Mm-hmm. Yeah. Yeah, they get lost, right? As an H. So oftentimes you're going to see a minus H where we lose the hydrogen. Okay. All right, so that right there is the M plus with the loss of a hydrogen. And so you'll see a -1 for the mass, which is losing the hydrogen, right? Okay, so this right here would be the other thing that happens quite often, which is whenever we generated the very positive acidic hydrogens and they went off onto an oxygen, what happens to them? We generated that H2O plus, right? Okay, and that is a very good leaving group, isn't it? All right. And so this right here is the loss of water, actually, and that's usually a very large peak in these. And so you get the loss of water. So 18, right? Okay. Everybody good with that right there? Okay. And then we get the alpha cleavage down here. So let's go and look at some of the alpha cleavages and the other cleavage in the alcohol. So the alcohol's molecular ion typically undergoes two major cleavages. We get the loss of a hydrogen atom. This is going to give you your M minus H peak. That's 1 liter because we lost hydrogen, which is 1, right? And then we're going to also get the option where we lose water. And so that's going to be the loss of the hydrogen on the most stable spot. And then we lose the OH as well, which gives you the water being lost. Okay? And that's the one we saw right down here. Okay. Let's talk about some carbonyl containing compounds. So we have in carbonyls a double bonded oxygen here. And so particularly we're going to have the molecular ion of your carbonyl containing compounds. It's going to produce by the loss of the lone pair non-bonding electron from your carbonyl carbon, and that's going to be your M plus right there. And then the alpha cleavage is going to be your most common fragmentation pathway, typically producing your base peak. And that's going to be where we fragment off on the other side of that carbonyl, losing the carbonyl part of the chain. And that's this one right here. And notice that that typically goes away with your positive charge. And that's going to be your MZ43 in this next spectra right here. So that's your MZ43 right there. Okay. All right. Again, by the way, what's the difference between these? Yeah, it's a methyl, isn't it? Yeah. So you're actually seeing the loss in the methyl off of that. Right there. Okay, so let's go ahead and look at a McLafferty rearrangement. So your molecular ion here of the carbonyl containing compound is going to undergo a cyclic movement of 6 electrons. This is going to give you an enol radical cation and an alkene. And so this is the alkene neutral fragment that's going to go down the pump. This right here is going to be the enol radical cation. And so we have here where it abducts the hydrogen, creating the OH+. This causes all the electrons to move over 1 onto that alpha position. And notice that right here is your enol radical. See the enol double bonded alcohol? Okay. Okay, let's look at the McLafferty rearrangement. So again, notice that this fragment here is what's usually lost here. And that's again going to be a 3 times 12, right? 36. And then plus another 6. So 42 loss, right? Okay. And so right here we see this McLafferty rearrangement. And we see that loss right there. Can everybody see the 42 loss? I'm sorry, not 42 loss. The here's the M plus, right? So again, we have this right here. We're going to undergo our rearrangement, creating the enol portion right here. Keep in mind that carbonyls is not just a single functional group, right? So it's going to be esters, amides. Amides have the nitrogen here, right? And carboxylic acids and aldehydes. Okay, and this is the rearrangement one right here. Mm-hmm.
So what's the difference between the M plus and the base peak for 60? It would be, you said 42?
Yeah, so this one right here would be 90 right here. So this is 80, what is that, 83, 82? I didn't write it down on here. So 90, oh, I guess that would be like 87, right? Okay. And so that's a 37 difference. This one was that amount of loss because of the loss of these extra carbons.
Oh, okay.
Yeah. So it'd be the specific number of carbons that you've lost here. Okay. And so what we'd always end up with is we would always end up with a multiple of the CH3 plus CH2s being lost. Okay. Okay. And again, whenever you do these maths, the numbers you want to keep in the back of your head is how much is a CH3 being lost? 15, right? Okay. CH2 being lost is 14, exactly. Okay. In this case right here, because we're forming this double bond right here, we're always going to end up with a CH as well. Okay. And so instead of getting the 13 plus multiples of CH2, which would give you an odd number, you always end up with an even number, or a number that'd be one less than the other, right? Okay. And so, for example, here we end up with, was probably like 87, I think. And so 60 there, that's 27. And so we've lost 13 and 11. So that's 24. I'm sorry, not 13, 15. And a 13. It's 2 off on each phone. So 15 and 13, 28, right? And that's actually the whole number. Yeah. So we lost 2 of these carbons. You can also go the other way if you want to calculate the other way of what's remaining, right? And so you would go through here and you have the oxygen, and you'd calculate the number of carbons remaining that's not taken up by those oxygens. Okay, so make sure you practice. Has everybody started the homeworks at all? No? God, you had like 2 days of nothing.
That's exactly what I did.
Gotta mentally prepare.
For the next week of nothing?
It's gonna be so boring. I gotta go.
Okay, so again, this is very much a practice thing. There's only so much I can do by guiding you through these, and let me know how you do on the practice, okay? Okay. All right.
I'll email you.
Sounds good. Okay. So when should you start homeworks?
Immediately.
Yeah, like 3 days ago, right? Okay. Okay. So, anybody have any questions before I go on to the next thing? Okay. Okay, fantastic.
Due this week, do we?
Huh?
No homework due this week.
No, I think I have any homework. I'd have to look. Yeah. I have 6 different classes to remember when the homeworks are. So. Yeah.